Yeah, okay. So I'm Samuel Goodwin. I live here in the Netherlands for 12 years or so now. I run a small consulting company, Roundwall Software, help companies fix apps, make apps, whatever. You can find me here on Mastodon. I'm not on Twitter or anything anymore, or you can just email me here. But we're going to talk about making our apps faster without having to spend money. Also, I haven't done this in literal years, and I can't see any faces from here because this light is extremely bright. So if I go like way too fast or something, just like shout or something, and I'll slow down. So you've been spending a lot of time building your app. Maybe you're really excited about what it's going to do to help people. It's going to be some awesome new feature, make you some money. Everyone's working really hard on it, but you get it out onto a device and it runs about like this. It's not very fast, it's kind of uncomfortable. You don't want to ship like this, I assume. So we're going to fix that. We have the technology to fix it. We don't have to spend money to do it because we already have the software necessary. And we don't have to fix it by trying to remember a set of rules about this is faster than this, so you should always do this, and you should never do this because that's slow. We can just find out exactly what the problem is and fix it. Once upon a time, this was slow. Just having multiple views in a table view cell like this was slow, and you would not scroll quick on like the original iPhone. But now this isn't really a big deal, so we don't need to remember this rule. We don't need to make sure that we flatten this down to just one view because that's not necessary anymore. So Apple gives us this. It's called Instruments. And this tells us exactly what's slow, exactly where the problem is, and we don't have to mess around anymore. There's a whole bunch of tools if you first open Instruments, and this is like kind of overwhelming. Most of these we don't need to care about a lot. Well, they're all useful, but initially, let's just worry about maybe 2 or 3 of them. So first, we're going to talk about leaks there. Leaks is for tracking like memory usage in your app. It'll tell you how much memory is being used. It will try to figure out where you have memory leaks, and it's super useful. When you first go to start the leaks instrument, one of the options you'll see is to enable NS zombie detection. This doesn't happen so much anymore because we're in Swift, but especially back in Objective-C, you would get zombies where you have deallocated memory, but you still have a reference to it somewhere, and that would result in undefined behavior, crashes, etc. So instruments can help you find those as well. Technically, this shouldn't be an issue in Swift, but I've still seen it because you're using iOS frameworks that are Objective-C, or maybe you're doing some weird C stuff underneath. So it's still worth looking for. So once you press record, there's going to be a ton of information, but don't worry because we don't need to pay attention to most of this right away. Sorry? Oh, okay. So the main thing we need to look at is this graph up here at the top. That shows how much memory our app is using. If that goes up over time, if that goes down over time, that's the important information. If it shoots up when you don't expect it to because you're just looking at a screen or you're scrolling and suddenly you're using 50 times as much memory, that's probably a problem. If you navigate to a screen, you should expect that memory goes up because now you need new stuff for this new screen. But then if you leave that screen and that memory does not go back down, then that's potentially also a problem because maybe then you're holding on to stuff that you don't need to anymore. You have a cache that's a little bit too aggressive. You're not being very efficient with your memory usage. You also want to check around in various parts of your app that if you press this button here in the simulator, the simulate a memory warning, that your app will actually reduce the amount of memory it's using. This is the system's way of telling you, like, hey, if you continue to use this much memory, we are going to kill the app. And that won't show up in your crash logs as a crash, it'll just terminate the app. So your users will think it crashed, but you won't be able to find the crash because there will be no crash log. So if you can reduce the amount of memory that you're using whenever this memory warning gets triggered, that will help. It's less necessary on modern devices as well because we have way more RAM than we did in the original iPhone, but it still comes up. So just below that first graph there is the leaks. This is whenever the system detects a memory leak. Like I said, the memory leak is where you have reference to memory that, well, no, sorry. A leak is if you do not have reference to memory anymore, but you still allocated it, so now you can't deallocate it because you don't have reference to it. This also happened a lot more in Objective-C, but it still happens in Swift because our underlying libraries are written in C, Objective-C, we're still referencing those things, and you can still, get yourself into trouble with Swift even. Another way to figure out what got leaked, because the leak detection doesn't always find exactly what leaked, is way, way, way down here at the bottom. There's a little button labeled Mark Generation. So that will record all of the objects that are in memory at that time. So you can press this button like right before an action, and then press this button again right after an action. And then you'll see multiple generations that you can compare. And so the system will then show you, here are all the objects that were created since this last generation, or here's all the objects that were destroyed since this last generation. So if you have a bunch of objects here that should have been destroyed and are not, those are the things that you leaked. So that was kind of a lot of information to start this with. So here's a picture of me finishing my driver's license test finally. In the Netherlands here, they brag. It's a 30% fail or 30% pass rate on these exams. So they make it really hard. It took me almost a year to finish this. Thank you for the applause. Okay, so the other important tool here is the time profiler. This is going to tell you exactly where your app is spending its time. Especially if your app is doing a lot or your computer is struggling to keep up because you also have Slack open while you're trying to do this. You might want to turn the recording mode to deferred, that second option there. That way it won't try to draw the graph and show you information while it's running. It'll wait until you've paused the run and stopped it. And that way your computer's not trying to process the data at the same time as recording it. If your machine's fast enough, you could probably just run immediate and it'll be okay, but I've run some apps that were doing enough work that it couldn't keep up. So what you're going to see once you hit record is kind of similar to the memory profiler, except for we're talking about CPU time here. So like you can see here, this is just me recording the initial launch of an example app. So we do some stuff in order to get that initial screen up, and then CPU should just go back down to 0. If this did not go back down to 0 when I expected, that would be immediate cause for concern. You can also see we track the thermal state of the app while this is happening, because if you use the CPU hard enough for long enough, it's going to make your phone warm. And a warm phone is burning battery faster, is uncomfortable in the hand. It's generally cause for concern. So if this is changing to something other than green, you have a problem. This instrument also will attempt to detect hangs. So this is any time that your main thread, which is the one that handles your UI updates, is paused for longer than, I think the default's like 150 milliseconds, but you can change that in the settings. Anytime that you're doing work that takes longer than about 16 milliseconds or so is going to result in dropped frames because your phone is trying to update the screen at 60 frames per second, or I think some of the newer phones it's like 120 frames per second, or it varies between them. But we want to keep at least 60 frames per second, let's say, and 60 times per second, 1/60th of a second is about like 16 milliseconds. So if we're doing work on the main thread that takes longer than that, then the system can't possibly get around to updating the screen fast enough. So the information it records is going to show you a ton of there's going to be a ton of information it's going to show you when it records. And depending on what you're looking for, we don't need to look at all of it. So they offer some filtering options. Initially, what I would almost always do is choose the option for hiding system libraries. We can't optimize what UIKit is doing. We can't make that go any faster, so it kind of doesn't matter how long that's taking. What I care about is how long my code is taking. If you're worried about UI performance, then we only really care about what's happening on the main thread. So we can also specify which thread we're looking at and say, don't bother showing me information that's not about the main thread, which is a lot less information usually. You can also click and drag on the graph itself and select just a region of the timeline. So you can say, well, I only actually care about what happened right when it launched, or I only care about what happened right when I pressed that button, or right when sync kicked in or something. And that way we're not looking at all this other stuff that doesn't matter. Sometimes this option is also very handy, the invert call tree. So you see the lowest, the deepest function in your call stack first, instead of having to drill down to it. Now with the remaining data, that's a little bit less overwhelming. We can dig through here to find what's going, how long, we can dig through here to find how long everything is taking. So for example, you could see here that my item list's body function, which is what SwiftUI is calling whenever it wants to recompute the list, is only taking like 2 milliseconds. Especially something like a body function, if it's taking more than just a few milliseconds, then you probably have a problem, because those get called often with SwiftUI. This is also where we want to look for any of those functions that are taking longer than the 16 milliseconds I said, because we're looking at the main thread here. So if for some reason that body getter or some other function that it called was taking longer than the 16 milliseconds, then that's a performance issue. One nice thing you can do here, you can save this recording and then go and change your code to make this faster, and then come back and make a new recording and compare the two. So you can not only say, like, yes, this is where it was slow and I fixed it, I made it faster, but you can say how much faster. Managers and your boss, they love that sort of thing. You can say, now the app launches 30% faster, now sync takes 20% or less time. There's also a search field way down at the bottom so that you can dig for a specific function that you're looking for. So if you're comparing on that second run to see if your body function's any faster, you can then filter through and not have to dig around for it. Because hopefully you made it slow, or hopefully you made it faster, so it won't be in the same place in the list that it was before. So by default, for each function call, it displays these two numbers, the wait and the self-wait. The wait is how long that function took, but the self-wait is how long it spent in that exact function. So if you have a function that calls other functions, then they will be consuming some of that wait and not the original function. So in this example here, this function takes 88 milliseconds, but only spends 2 milliseconds of it inside itself, and the rest of that time is in functions that it calls inside itself. Also, if you double click on functions in your code, especially ones that you own, then it will show you in your code where that is. So we can see this function, this load contributions, most of the time is spent in this one async call, which is weird because we're filtering for the main thread, and I would assume this async parse data is happening in the background. Turns out it is not. If I look for that same function in the list, I can see that, yeah, actually it's happening on the main thread. It's taking a substantial amount of time. This is not what I expected. If you dig in the code, you'll find that this view model is marked with main actor. So this async function is technically async, but it's still happening on the main thread and not in the background where that work should probably be happening. This is where you have to go back to your team and say, maybe we didn't understand actors the way we thought we did. Maybe this async stuff is a little bit confusing, and we need to do it differently. Sorry, hold on. There's a little toggle switch just above your data there that also lets you choose to look at things divided by threads. Here I can see that most of the work on launch is actually happening on the main thread. A little bit is happening on some background threads. It's quick to tell from here that the app is doing a ton of work. Well, if the app was doing a ton of work for a long time on the main thread, it'd be really easy to see. You can also get a sense for how well the work that you're doing is spread across threads if you are doing background work. It would be a problem if I saw that the background thread was doing a lot of work that I did not expect, but also if it wasn't spreading that out the way I expected. We can also look divided by CPU core, because maybe you have things split by threads, but if all those threads are assigned to the same core, then you're not actually making efficient use of the fact that we all have machines in our pocket with, what, 16 cores or something ridiculous now? So here we can see that actually the work is spread kind of nicely across them all. This is a common occurrence. If you have a lot of background work and you think you're spreading it out, you can get what they call like a snake graph, I've heard it called, where work is happening on different CPU cores, but it's happening sequentially. This is not actually multitasking the way we think it should be. Ideally, we want the work to look more like this, that if we have work that we can split up across multiple cores, it can happen all at the same time, and then we can just get the result at the end. So yeah, this is a picture of my new bike, the first time I took it to a gas station. Don't worry, I did not put diesel in the tank. A lot of people warned me about that. Just figured we could use another little pause. That was a lot of stuff. Get some water, actually. So now you know where the information is. Now you know how to find it. Just in case you're a little bit lost about what to do with all this information, here's my overall strategy I deal with for improving the performance of an app. First, we find out what's slow. Then make it faster. You could try whatever you want to make it faster, and then just run the measurement again, and you'll see exactly how much faster it is. If somebody tells you some weird trick is going to make things go faster, you try it. And if it is faster, great. And if it's not, then you can show them that it's actually slower. We don't have to have like debate or argument about whether or not you should do things a certain way. You can just look at the graph and see. In some cases, though, we can't make things go faster. So that's the kind of work that needs to happen in the background. And like my example, we need to make sure it's actually happening in the background and not just asynchronously. This is probably going to include things like network access, database access, all that sort of stuff that takes time. And if that doesn't work, especially if it's something like an Apple function that you can't optimize because we can't change Apple's code, you can at least try to make it happen less often. So an important trick with especially UI stuff, every time Swift UI, for example, needs to recompute the screen, that takes a certain amount of time, and there's nothing you can do about it, really, except for try to make it happen less often. So if you see that that's what's being slow, is actually the Swift UI is recomputing and spending a lot of time recomputing the view, we just need to figure out how to make that happen less often, because we can't actually make that go any faster unless you join Apple and get on the team. Yeah, I mean, they hire people a lot. A lot of people I know now work for Apple or used to work for Apple, or you could probably get in. So that's all I have to share. If you have any questions, please feel free to come ask. I have like I call it like a resting serious face. So whatever it looks like here, it's totally fine to just come and ask me anything you want. If there's any questions now I can answer, or if you have like specific examples later, if you have your laptop around, like I'm happy to look at whatever you've got going. Are there questions now, though?
Thank you. So I want to call out a couple of the other instruments that weren't shown. If you're moving to Swift 6, the concurrency instrument is invaluable. Among other things, you can see as your calls move from the main thread to a background, and you can see things move around, and
Yes.
you can often use that to help you optimize and things that you think you're doing right, you aren't, and it'll point you in the right direction. The Swift UI is a very valuable instrument because Swift UI views are views. They're not reused. They're created and thrown away often, and so the number of allocations, if you just use the allocation instrument, seems to go up, even though they've been thrown out and recovered and they're not really taking memory anymore. So the Swift UI instrument's another great one to use. For drawing, sometimes using and seeing if you're costing too much by having things that are opaque, or the drawing is using too many layers and you're getting slowdowns there. So there's an awful lot of help from these depending on what you're working on. So I urge you to take a look around. Do you guys know James Dempsey? He does James Dempsey and the Breakpoints. He's currently piloting, it just started last night, but you might be able to get in. He's currently piloting a class on instruments where in 8 sessions he's going over a lot of these different instruments. And so that's something you might look for. Questions that you might have?
Yes, I have a question. For Swift UI, the body recomputes a lot of time, and we can look at it through the instruments. But is there a way to look at which views were the ones getting re-rendered when the body was recomputed?
Yeah, that's what the Swift UI instrument is for. I didn't get into that one because I wanted to make it just the bare minimum necessary to get started. But that would be where we would look at the Swift UI instrument.
The other thing is there's the underscore print changes, and that's really useful. It tells you what's been redrawn and why, and it helps you see that this body really needs to be broken up into other views so that only the view that changes is redrawn.
Yeah, that'll tell you the cause of the redraw, yeah.
Another question?
No, that's it.
Okay.
No more hands.
Please thank Samuel again.
Yep, thank you. You're good.